Hello, ma'am. Ma'am, can you hear me?
Yes, Akshita. So now listen
Okay.
over here. Yeah, coming back to the topic. What we have discussed today, we were on the E2 topic, right?
Yes.
And quantum nature of light we are about to discuss. Okay. So as I had told you that the energy levels are quantized in nature, if you are aware. Done. So tell me, yeah, how will you define it? What do you mean by quantization of the charges?
It can only be by the numbers of n number of particles. Like you said this
Hmm? See?
like it can be only like n like a whole number. It can't be like 0 by 4, 1 by 3, like that.
Okay, fine. So basically, they are dependent on the quantized energy levels, that is the multiple integral of the energy shells. Okay,
Yes, ma'am.
so this is the theory. Now over here you have to define the photoelectric effect, and yesterday I had shown you the zinc metal uh, plate experiment, remember, and I had told you to see the videos for this, correct?
Yes, ma'am.
Even I had shown you one video, so have you seen that?
Yes, ma'am.
Okay. So now consider one ultraviolet light, okay, that is shining on a negative charge plate. This is what I had told you, right?
Yes.
So the light will cause the charge to leave the plate. Okay. Why? Because what happens here is that whenever the charges gets attracted towards the from the zinc plate to the ultraviolet light, it actually leaves all the charges from the surface. Done. Why? Because their frequency matches. Okay.
Yes, ma'am.
The light, which is that is the ultraviolet light, when you fall it on the zinc plate, the frequency of your particular ultraviolet light and the free electrons on the surface of the zinc plate matches their frequency, and hence they come out of it. Done. So
Yes.
let's take one example also. Imagine that we are having a ball, okay, that is floating near the edge of the swimming pool. Okay, let me show you the diagram for this. This chapter is more about theory, so no need to worry about that. Okay, just listen. Okay, so here, if suppose you are at the other side of the swimming pool, what will happen? You could get the ball out of the pool by sending the waterways towards it, correct? And
Ma'am.
to get the ball out of the pool, you can also need to lift the ball as high as the edge of the pool, correct?
Yes, ma'am.
Okay, so we must give it a thought that the we must give it basically enough potential energy so that it could reach its height. Okay, and also we can do this by making the amplitude of the wave very high. Done. And if the amplitude is not high enough, the ball will not be able to leave the pool. Understood? And
Yes.
unless we build a machine, suppose that we collect the energy over a period of time. Okay, then what will happen? So in this case, there will be a time delay before the ball gets out. Making sense?
Yes, ma'am.
Yeah, I'm saying that if suppose the amplitude is not high enough, then what will happen? So if your amplitude is not high enough, the ball will not be able to leave the pool. Why? Because it will not be able to jump out of the boundary. Making sense?
Yes, ma'am.
So for that, we build a machine that will collect the energy over a period of time. Okay. And hence in this case, the time delay before the ball gets out of the pool. Done. So when
Yes.
we relate this to the zinc plate experiment, what we can say that electrons will be emitted from the light source, which is very bright in nature. So the brightness basically related to the amplitude of the wave. Making sense?
Yes, ma'am.
And if your source is suppose very dim, then we can expect that no electrons will be emitted out of it. Correct?
Yes, ma'am.
Okay. And if suppose the electrons got emitted, we can expect a time delay before the atoms collect energy from the wave.
Yes,
I'm
ma'am.
saying if the electrons are emitted, then we can expect a time delay. What time delay? That the atoms collect the energy from the wave and then they emit out. Making sense?
Yes, ma'am.
Okay. And if we lower down the frequency of the light, the electrons will still be emitted if it is bright enough. Making sense?
Yes, ma'am.
Okay. Now here, let's have a look at the zinc plate experiment. So as we had seen yesterday also, but still I will show you the picture that is of the zinc plate experiment. Let's have a look over this. Check. So this was the zinc plate experiment. Okay. What happens here is we have a zinc plate and electroscope is there. Okay. When we shine the ultraviolet light over it, then the electrons are emitted. Done. And charge will be lost and the electroscope gold leaf will fall. Making sense?
Yes, ma'am.
Okay, so the result is not entirely as we are expecting. Let's have a look what the results are. Okay, tell me any doubts in the experiment.
No, ma'am.
Okay, I'm saying that zinc plate on an electroscope is put. Okay, now when we shine the ultraviolet light over it, the electrons are emitted out. This shows that the charge are lost from the surface. From the electroscope, gold leaf will fall down. Here is your gold leaf. You can see it is in the gold color. Okay. And the results that we are obtained. These are the expectations, hypothesis that we have made. Understood? Now let's see
Yes,
at the observations. What do we observe? So we have observed that the gold leaf means it actually goes down and it indicates that the electrons are emitted from the surface of the zinc plate. Understood?
yes, ma'am.
I'm saying if the electrons are emitted out, the charge will be lost. Okay.
Yes, ma'am.
The gold leaf goes down. Sorry, my bad. I'm really sorry. Yeah, I was telling that the gold leaf goes down, which indicates that the electrons are emitted out from the zinc plate. Making sense?
Yes, ma'am. Yes, ma'am.
Why? Because as yesterday we had seen this thing that if suppose here we have the battery eliminator, from here I am bringing one terminal over here and the second terminal I am bringing it over here, this circuit gets completed. Done. But as soon you flash on the lights, all the charges are trapped. They just evolve out of the plate and hence the charges which were making a track out of it, hence the leaf will go down because now it does not have any charge. It was flicked over here when it was having the charges because it was making a complete circuit. Making sense?
Yes, ma'am.
Any doubts?
No, ma'am.
Sure.
Yes, ma'am.
Okay. Check. Is it visible?
Yes, ma'am.
Okay. Now let's have a look from the start. So basically this is the electroscope. This is the electroscope. Gold leaf electroscope. Here is the gold leaf attached. Okay. Here we have two terminals. One is positive and one is the zinc plate, making it negative. Any doubt still here?
No, ma'am.
Great. Now check what is happening. He put a zinc plate over it. It is charged. He had rubbed it. Correct?
Yes, ma'am.
Now he is connecting the positive terminal over here and negative terminal over here. Now check. This is ultraviolet lamp, which creates the ultraviolet light. It's a very bright color. That's why it is blue in color. Check. What does the blue color signify? Brightness. Okay.
Yes, ma'am.
Why you are so down today? Everything okay?
No, I was just a little bit tired today. Like,
Tired due to you just came from the school.
No, I had like more classes from the morning. So
So same here is going on, Akshita. It's okay. Even I am facing my exam days because all of my students are giving exam in May and June month only, right? So what I am having is I am teaching
yes,
from morning 8 o'clock till night till 9:30. You can say, okay. So don't worry. Be mature because you have to face it. Okay, it's just a 2 months of that thing.
okay,
Okay, let's continue. So it's a brightened light. Done. Now see what he will do. He will turn it on. That means the charge is going till here. Correct?
yes, ma'am.
Till here the charges are going. But now
Yes,
it is not connected. So from here the negative plate is carrying negative charges. Here the positive charges are there. So they will start flow through towards the plus electrode. Making sense? Now check
yes,
when he brings the negative terminal. Check. Is it?
yes, ma'am.
See, it got deflected.
Yes, ma'am.
That means the charges are here.
Yes, ma'am.
Normal light will not make any difference. Check. But the ultraviolet light will make a difference.
Yes, ma'am.
Now see. This is the ultraviolet light now. It will
Yes,
come back because it had absorbed it had knocked out all the electrons from the surface. Okay. So now there is no connection. Again it got deflected. Again it will come back. Check. Making sense?
yes, ma'am.
Any doubts?
No, ma'am.
You want to ask anything?
No, ma'am.
Okay, very good. So let's come back to the topic. This is what I was explaining you. Let's have a look at the postulates of this. So the postulate says us that the gold leaf will go down, indicating that the electrons are emitted from the surface of zinc plate. This is the first observation. Second observation, the gold leaf will go down even if the ultraviolet light is very, very dim, because dim light, the leaf takes longer time to go down, but there is no time delay before it starts to drop. Making sense?
Yes, ma'am.
In the initial time, it will show no drop. Means no delay in the drop. Okay, sorry. Understood or not?
Yes, ma'am. Yes, ma'am.
So if the light of lower frequency, let's say the visible light is used, the leaf will does not go down because it shows that electrons are emitted, and this is the case even when very low intensity of the light is used. Do you want to write the observations?
Yes, ma'am.
Shall I show it to you?
Yes.
Because this is a theoretical chapter, so observations will come. So this is the observation for the gold leaf experiment. Okay? Do you want
Yes,
to
ma'am.
write it?
One second, ma'am.
Or let it be? You can write it later on. I had shared the board already.
Okay, okay, ma'am.
Okay. So the quantum model of the light. Let's have a look. What was the quantum model of the light after this? In the quantum model of the light, light was made up of packets, which is called photons. Correct?
Yes, ma'am.
Now each photon gives one energy wave. Correct?
Yes, ma'am.
Which is proportional to its wave frequency. Correct?
Yes, ma'am.
Okay. Now, each photon belongs to one wave which is having energy E, and it bears some frequency, that is F. So, the energy that wave bears, the photon, is directly proportional to the frequency it have. So, it is directly proportional to X. When we convert the proportionality symbol into equal to, we will get H, which is known as your Planck's constant value. Nothing but 6.63 into 10 raised to minus 34. Okay.
Yes, ma'am.
and the SI unit is joule second. Any doubts?
No, ma'am.
Sure.
Yes, ma'am.
Okay. So this was the equation that we have. Now the intensity of this light is related to the number of photons. Okay. That is not the amplitude as it was there in the classical mechanics. In the classical mechanics, we say that the intensity is directly proportional to amplitude square. Right? But
Yes,
in quantum mechanics, in classical mechanics, what we said? That the intensity is directly proportional to amplitude square. But in
yes,
quantum, we will say that the intensity depends upon number of photons. Okay. So higher the number of photons per unit and area per unit length per unit time. So higher will be the intensity of light. Okay. In quantum, it is actually the particle model. In classical, it is actually the wave model. So this is wave connected. This is particle connected. Making sense?
yes, ma'am.
Okay. So the ultraviolet light has a very high frequency. So when the individual photon of ultraviolet light is absorbed by the zinc plate. Okay. Ultraviolet light has a very high frequency. So I'm saying when the individual photon of your ultraviolet light gets absorbed by the zinc plate, it gives out enough energy to the zinc electron. Okay.
Yes,
To
ma'am.
enable it to leave the surface. Making sense?
Yes,
Okay.
ma'am.
Shall I show you the postulates again? You want to?
No, ma'am. I got it. I'll just write these.
Yeah,
Snippets.
wait, I'll show you the postulates also because these are important things. What were the observations? So check. Ultraviolet light has a very high frequency. Done. So when the individual photon have the ultraviolet light which is absorbed by the zinc plate, it will give out enough energy to the zinc electron that enables it to leave the surface. Now, when the intensity of the light is low, there is not many photons, but each photon will have enough energy to enable the electron to leave the zinc plate. Okay.
Yes, ma'am. Ma'am?
Okay, I'm sorry, Akshita, that was a technical glitch. Okay.
Okay.
So, am I audible to you?
Yes, ma'am.
Okay. So, let's come back to the topic. And I was explaining you that. Okay. So, what I was explaining that these are the postulates. Okay. Now, let's
Yes.
come back to the topic. Next is Millikan's photoelectric experiment. Okay. Now, let me show you the Millikan's photoelectric experiment. Somewhere it is like this. Okay. Let's have a look. In this experiment, what does he did? He had provided a potential, okay, which is connected to the anode and cathode. Okay. At anode, he placed a metal plate. At cathode, he placed a collector. Okay. Inside a vacuum tube. Making sense?
Yes, ma'am.
Okay. Now, at this plate, he had provided a high potential. High potential will give out the free electrons on the surface. Correct?
Yes, ma'am.
It will provide the free electrons on the surface of the metal. Now, this metal plate is also connected to the potential divider in parallel with the battery, okay, which is connected to a ammeter, and it will check that how much current is going, and it will complete the circuit from negative terminal, that is from cathode to anode. Any doubts in this experimental circuit?
No, ma'am.
Check if you want to ask anything. Just check.
Okay, ma'am.
Is it okay?
Yes, ma'am.
Sure.
Yes, ma'am.
Okay. So now let's come back to the topic. What I was telling is that he had devised an experiment to calculate the kinetic energy of the photoelectron. When they are traveling from here to here, he can calculate. We will see that part also. Okay. Now here he is having a source which is having different frequency of the light range, so that whichever is suitable will knock out the electrons from the metal surface. Any doubts?
No, ma'am.
Okay. As soon he flashed the light of different frequencies, electrons start evolving in the vacuum tube and it got collected at the collector. Okay. Fine. So
Yes, ma'am.
here it's showing that the track is bouncing back. Why? Because these are electrons. Collector is also the cathode ray. Cathode ray is basically negative in nature. So the negative and cathode will going to repel each other and hence it will come back here on. Making sense?
Yes, ma'am.
Okay.
Excuse
Now
me,
let
ma'am.
me show you this part also. Just give me a second.
Yes, ma'am.
Check. Is it visible?
Yes, ma'am.
Is it?
Yes, ma'am. I can say it. The video, right, ma'am?
Yeah, it's a Millikan experiment he's doing. This video is visible, no?
Yes, ma'am.
Okay. different. Okay, yeah, this one is the correct. So all wrong.
Is it in is it in French? No, the subtitles.
Okay, understood.
Yes, ma'am.
How much? Half enough?
Yes, ma'am. Light is both a particle and a wave.
Yeah, particle and wave behavior, duality of that. Okay, but you can watch this video because we are not having. You can watch this video and you can get a deep knowledge of this. Okay, so now let's
Okay.
have this experiment. As I told you, light when flash on it, the electrons will come out of it. Now let's see its postulates. Okay, so as we are aware that the light from the source is having a known frequency, correct?
Yes, ma'am.
Okay, it passes into the apparatus through the small windows. Okay, and where is the small window? Akshita,
The small window is
it's
uh
here. Check.
pin.
This is window. Light is coming in from the window. Okay, understood now?
Yes, ma'am.
Okay. So if the photons of enough energy, electrons will be emitted from the metal sample. Okay. If it is, what I'm saying is, if the light from the source is coming into the apparatus from the small window, what happens? The photons, if have enough energy, the electron will emit out from the metal surface. Okay. And some of the electrons travel across the tube to the collector also. Okay. Without being emitted. So it causes a current to the flow of the circuit. Why? Because one is plus, one is minus terminal. So now the current can be measured in the microammeter. Done. Here potential divider is also been selected and it is adjusted until none of the electrons reach the collector. Okay. And also the law of conservation of energy has been applied, that the kinetic energy of the fastest electron, which is just stopped by the potential divider or the difference provider, will be calculated as loss in the kinetic energy and gain in the potential energy. Okay.
Yes, ma'am.
Okay. Putting your brain into the syllabus. Are you into the topic or is just going like that?
I am into the topic.
Are you sure?
Yes, ma'am.
Okay, fine, as you say. Okay, so what I was telling is, we can give the kinetic energy of the fastest electron which is coming out of your metal sample. Okay, how you can calculate? You can calculate that if the electron got stopped over here, so this kinetic energy converted into potential energy, as this is also negative in nature, so this is repelling the electron. Okay, so we will calculate the loss of the kinetic energy is equal to the gain in electric energy.
Yes.
Okay, now let's have a look what is that. So basically this is half mv square and this one is drift velocity of the electron multiplied by the charge. So this will be the electrical energy. Okay, now the maximum energy can be calculated as V, that is coming from the source, multiplied by S, where V is the velocity which is coming from the source. Okay, now the light source also changes, one with a different frequency. Okay, and the procedure is repeated. Okay, basically
Yes, ma'am.
what I said, that the light source now will change. Okay, with one of the different frequency, it changes now. See here, different frequencies are there.
Yes, ma'am.
So as soon it changes its frequency, the whole process repeats itself. Okay, now let's have a look at the graph of it. So basically, if this is a graph, here I am having potential. Small v is velocity, capital V is potential. So from here somewhere, let's say V from the source, which is coming out of from the source, the velocity of the light. Okay, so the low intensity will be drawn something like this, high intensity will be drawn something like this. Understood?
Yes, ma'am.
Okay, so this is high intensity ultraviolet. This is low intensity ultraviolet. Okay.
Yes, ma'am.
Now why it is in minus region? Minus region shows us that the velocity versus this one is current. You just need the velocity of the electron to be matching with the velocity of the electrons which are coming out of the zinc plate, or here is the metal plate. Okay.
Yes, ma'am.
Okay, now let's see one more thing. There is a minimum frequency required, Akshita.
Yes, ma'am. To emit
There is a minimum frequency required with the help of which the electrons can come out of this plate.
yes.
Okay, that
Yes.
frequency is brought by the source light. So when this source light brings out that frequency, it is known as threshold frequency. Okay. And it is given as F naught. Till that frequency, it will not come out. But at threshold frequency F naught, it will come out and it will run like this. This one is my frequency. This one is my Emax.
Yes, ma'am.
Okay. Any doubts?
No,
So
ma'am.
higher the energy you are providing, higher will be the frequency of the waves you will get. Okay. So threshold frequency means what?
The minimum energy required to emit the light photon.
Yeah. The minimum energy required to knock out the electrons from the metal surface. Okay. Now let's have a look at the photoelectric equations also. Fine. So I had told you that there is some Emax due to which, okay, this particular region in which the frequency is low than the threshold frequency is basically known as phi region.
Can I repeat, ma'am?
Phi region. Okay.
Okay.
This region I'm saying. Okay. So now after this, how much is the maximum energy? HF minus phi. Okay.
Yes, ma'am.
Phi is nothing but the work function. That is the amount of energy required so that the electron can knock out from the metal surface. Okay.
Yes, ma'am.
So if suppose I am not providing, if I am saying that my threshold, at my threshold frequency, if the photon has only that much enough of the energy of the electron that it can come out of it, so it will have zero kinetic energy. Okay, electron just came out of the surface and now it cannot travel. So it will have zero work function. Sorry, zero kinetic energy. Work function is there, kinetic energy is not there. So zero will be the kinetic energy and hence you can write it as E max equal to 0 equal to HF naught minus phi. Okay.
Yes, ma'am.
Fine. So this one is phi now. Okay. Now here need to be understood as my E max I told you is 0. So what will happen? My HF naught will be equal to my work function. If your energy required to bring out the electron from the surface is 0, then your work function energy and your frequency of the electron both will have same energies. Okay. So as I had told you that my E max is equal to HF minus phi. So from here, if I apply the value of this, I will get HF minus HF naught. So this is your E max values. They can ask the questions from this equation. Okay. Are you there? Akshita, are you there?
Hello, ma'am.
Yeah. Am I audible?
Yes, ma'am.
Okay, is it okay now?
Yes, ma'am.
Okay, so fine, let's continue. What I have explained, just have a look over that.
Yes. When Emax is 0, then HF will be that thing. And then after that, Emax HF minus. Can you
Hmm.
explain the last part, ma'am?
Yeah, sure. I'm saying if your maximum energy is zero, there is no kinetic energy. That means when the light came, it has the frequency that it can knock out the electron. But it does not provide it the energy so that the electron can travel. So the kinetic energy will be zero.
Yes, ma'am.
So it will be equal to HF naught minus phi. This is what our equation says.
Yes, ma'am.
Okay. So HF naught minus phi. So it will become equal to each other. When I apply this to the equation HF minus phi, so phi value is HF naught. So even I can write it over here HF minus HF naught. Okay.
Yes, ma'am.
Any other doubts?
No, ma'am.
Sure.
Yes, ma'am.
Let's do the next topic, that is the wave nature of the matter. I had already explained you the wave nature of the matter. Do you want to do it again?
No, ma'am.
Yeah, wave nature we have already discussed. So no need to go for that. You can have a look in the videos for wave nature and particle nature. Because again and again to explain this, I think it's stupidity.
Yes, ma'am.
Okay. I can show you the diagram and I can explain it in short to that.
Yes, ma'am.
Yeah, there. So here I'm having a heater supply. Okay. Then here it is a hot filament which gets heated via this. From here, what will happen? Accelerating potential has been applied. Here I have the anode. Again, this is acting like a cathode. I had connected a acceleration supply, which is nothing but your battery. So this much of potential is created. It is high potential, it is low potential. So it will generate the particles with v velocity. Okay.
Yes, ma'am.
Please watch out the video for this. This will give you how the wave nature has been explained. Okay. So from
Okay.
this, we can even calculate the particular speed of the electrons. Okay. How? By using the conservation of energy law. Again, there are loss in the potential energy is gain in kinetic energy. Now it is moving. Check. It is moving in nature. Okay.
Yes, ma'am.
Just the vice versa of the first process. In the first process, what happened? I had told you just provide the mechanism that much frequency that it knocks out the electron but does not have energy to travel after that. So my HF minus HF naught is equal to what? 0. Understood?
Yes, ma'am.
Hence my HC equals to phi will be the equation. Correct?
Yes, ma'am.
Anything you would like to ask from here?
No, ma'am.
Great. Now listen. So what happens in the wave nature? This is a hot filament. It will release the wave. That will come out of this window with velocity v. We can check it. Done?
Yes, ma'am.
Okay. Now after this, if you have an issue, please ask.
No, ma'am.
Okay. So how you can detect the electrons? Okay, in any particular experiment. So you cannot see electrons directly, but you need a detector for it. Okay, as we have seen in all the experiments. Correct. So the
Yes.
electrons basically collide with any atom, and the atomic electron energy is seen as the spark. Okay, which is known as the phosphorescence. Okay, the
Yes.
process is called the phosphorescence, and it is used basically to see where the electron land is there. Okay.
Yes.
Okay. So now zinc sulfide is one of the best substance which is used to coat the glass screens to that area or to that light when it is emitted out, where the electrons build with the screen. Done?
Yes, ma'am.
Okay. Now there are some other type of TV screens also, like your small mosquito window, correct?
Yes, ma'am.
Yeah. So you must have seen that TV screens also release the electrons. Okay. And then this phenomena, what do we call it as? The aurora, something. Okay. So this aurora is also a resultant factor of photoelectric effect. Okay.
Yes, ma'am.
That the resultant you will see bright color, dim color as per the frequency getting interacted with the free electrons or free charges in the surrounding. Okay.
Yes, ma'am.
Done. So now here, the diffraction pattern. We have already studied the diffraction pattern, but let's just repeat it once. Okay.
Yes, ma'am.
So Akshita, I'm giving you a question. Please solve it. You need to be very quick, but again, we will not waste much time. Please solve this question.
Volume of sodium is concentrated by light of wavelength. Maximum kinetic energy of the photon.
Yeah.
No, ma'am. No, ma'am. I was just reading the question.
Kindly be quick,
Yes,
Akshita.
ma'am.
And this chapter is over.
Okay, ma'am.
Yeah. Are you done?
One second, I'll answer. One second.
Kindly be quick.
Yes, ma'am. One second. Ma'am, I have done the first 3 questions. A is 9.6 into 10 to the power minus 20. B is 7.109 into 10 to the power 14. C is 3.75 into 10 to the power minus 19. I'm doing the D question D, ma'am. Ma'am, last question is 5.65, 5.66 into 10 to the power 14. Hello, ma'am. Hello, ma'am. Can you hear me? Ma'am? Ma'am? Hello, ma'am. Ma'am, can you hear me? Hello, ma'am. Ma'am?
Yes, Akshita. Yes. Yes, it's
Uh,
audible. Yep.
Yes. I told you the answers. Did you hear them, ma'am, or should I repeat the answers?
No, I heard them. I actually checking with the book, textbooks.
Okay, ma'am.
Okay. Yeah. So this is it for the day, Akshita. Let's continue tomorrow. Done?
Yes, ma'am.
Done. Okay. Bye.
Bye, ma'am. Thank you, ma'am.
Yeah. Bye.